Hi, in this video, we're going to talk about the big O notation. This is a very important topic as far as algorithm performance goes. So, as the previous example shows, and by that I mean this example here, that it's actually it's not important to know what Tn is precisely, right? Uh, what's important to know is that we know Tn is proportional to n in this case. So what that really is we want to know, it's good enough to know Tn is on the order of some function. And that's what kind of in a general sense what big O notation is. Now the big O notation actually has its roots in mathematics, so it predated computer science. In mathematics, the formal definition, and I do have to present you with the formal definition, is that the time t of n is on the order of f of n, or big O of f of n, if and only if, for certain constants c and n, 0, Tn is less than or equal to f of n multiplied by the constant for some n that is, or not for some n, for all n's that are bigger than some constant n0. So I know that's a mouthful, but informally it's actually trying to say something very simple. Basically, it's just trying to say the time n is never going to grow bigger or faster than f of n for sufficiently large n. Or if you look at it the other way around, is that f of n is an upper bound for t of n. And if you want to see it, what it looks like pictorially for a linear function, it's so t of n is a linear function. It's just a line. So f of n will be an upper bound for it. And so we just say t of n is really big O of n. Again, for the largest function that we wrote. So we said big O is the upper bound, and there are actually other bounds as well. So these are the definitions for other bounds. So there is the omega. Okay, and here's the definition. I'm not going to read that. And then there's the theta, and then there is little o, in addition to big O. These are the formal definitions again, and if you like, you can read them more carefully. But informally, what the omega provides is that omega just provides a lower bound, kind of versus the big O, which is the upper bound. Okay, and theta provides an exact bound. So it's neither upper nor lower. Lower is exactly what it is. And then finally, little o is actually very, very similar to upper bound. So it is the upper bound, except that I don't know if you remember that big O is less than or equal to, then little o is actually just less than. So little o still provides the upper bound, but Tn is never exactly the same as f of n. So anyway, I thought to just mention those because it was also mentioned in your readings. But for us, we will focus on just big O, and for very good reasons, because for computer science, the big O notation is used to classify algorithms according to how their runtimes or space requirement grow as the input size grows. And that is according to Wikipedia. So I want to draw your attention to the word classify. Okay, so what big O is basically there are classes of algorithms, and then we just want to kind of put an algorithm in one of these classes. So we've already kind of deduced or derived on paper, and as well as shown that the time for the largest function is constant times n plus another constant. So what f of n in this case is really just n, as we already saw, right? At c and f, they are not important, so it's really just n. So the largest function is classified as big O of n. It's a linear function. So these are some common classes of O of n. O of f of n in computer science, sorted kind of in the order of increasing rate of growth. So the first one is O of 1. That is a constant growth. So, and that is this line here. Basically, as the size of the input increases, the time it takes to solve for a problem, in using that class of algorithm, it doesn't increase. So it stays constant. So, and the next one is kind of log of n. And log of n, as you kind of see, is this red line here. It grows, but doesn't grow terribly fast. The next one is n, and that's linear, and that is one that we already saw. That's the in the largest function. So that's basically a straight line. It's linear here, the blue line, right? And the next one is n of log n. Well, there it is not plotted out here. We're going to see this a lot when we get to sorting. The next one would be n squared, or called the quadratic. It's kind of your quadratic formula, if you remember, right? And that growth rate is this kind of a purple line here, and that this kind of function starts growing really fast. And the same thing for n of n cube. N cubes is really kind of a shooting up here, growing even faster than n squared. Now, n to the basically any kind of a polynomial here, they are all kind of classified similarly, but these two do have different names. And then finally, there is the 2 to the nth power. That's called exponential. And these kind of things grow really, really fast. It's actually not this line. This is a polynomial, n to the nth power. Anyway, we will study examples of many of these.